The universe, we were told, was dying. Not in a dramatic, fiery cataclysm, but in a long, cold, agonizing whimper. The standard model of cosmology, carefully assembled over the last 3 decades, painted a picture of a heat death, a future where galaxies are pushed apart so fast by an unrelenting, constant force called dark energy that they eventually disappear from each other's view. Stars would burn out, black holes would evaporate, and the cosmos would become a vast, empty, freezing void. It was a lonely, static ending for a magnificent universe. But in the last 20 months, that story has begun to unravel. As we settle into 2026, the field of astrophysics is in the midst of its most significant upheaval since the discovery of cosmic acceleration in 1998. New data, first from the Dark Energy Spectroscopic Instrument, or DESI, and now corroborated by early returns from the Euclid Space Telescope, suggests that the constant in our equations is not constant at all. Dark energy, the mysterious engine comprising nearly 70% of the universe, appears to be weakening. The vacuum is losing its power. If these findings hold, and the statistical significance is climbing perilously close to the discovery threshold, we are not heading for a big freeze. We may be heading for something far more complex, potentially even a big crunch. The universe is not a static machine winding down. It is a breathing, evolving entity, and it seems to be exhaling. This is the story of the waning vacuum. To understand the magnitude of the current crisis, one must appreciate the fortress that is being besieged, the lambda CDM model. For nearly a century, Albert Einstein's cosmological constant, known as lambda, has haunted physics. Originally introduced to force his equations to create a static universe, Einstein later discarded it as his greatest blunder when Hubble discovered expansion. But in 1998, 2 teams of astronomers studying distant supernovae found that the universe wasn't just expanding, it was accelerating. Gravity should have been slowing things down, but something was pushing back. Lambda was resurrected to explain this push. In the standard model, dark energy is the energy of nothing, a property of empty space itself. As space expands, more vacuum is created, and since the energy density is constant, the total push gets stronger. It is a runaway train. The equation of state parameter, denoted as W, defines this push. For a true cosmological constant, W must be exactly -1, not -0.99, not -1.01, exactly -1. For 25 years, every measurement we took, from the cosmic microwave background to supernova surveys, circled around -1. The error bars were large, but -1 was always comfortably inside them. We became complacent. We assumed the vacuum was rigid. Then came DESI. Perched atop the Mayall telescope at Kitt Peak National Observatory in Arizona, the Dark Energy Spectroscopic Instrument is a marvel of modern engineering. Unlike traditional telescopes that take pictures, DESI is a hive mind of 5,000 robotic positioners. Every 20 minutes, these tiny robots rearrange fiber optic cables to point at 5,000 specific galaxies simultaneously, capturing their light to create a spectrum. This spectrum allows astronomers to measure redshift with exquisite precision, effectively mapping the universe in 3D. By mapping the distribution of millions of galaxies, DESI measures baryon acoustic oscillations, or BAO. These are frozen sound waves from the early universe, a cosmic ruler of a fixed length, about 490 million light-years. By seeing how big this ruler looks at different distances, and thus different times in the past, we can measure the expansion rate of the universe at specific epochs. The first cracks appeared with DESI's Year 1 data release in April 2024. The collaboration, involving nearly 1,000 scientists, released the largest 3D map of the universe ever constructed. When they fit their data to the standard model, it worked fine. But when they allowed the value of dark energy to vary over time, a model parameterized as W0, WACDM, the fit improved significantly. The data hinted that in the deep past, over 7 billion years ago, dark energy was effectively stronger than a cosmological constant, a phantom phase where W was less than -1. But in the last few billion years, it has transitioned to a weaker state, where W is greater than -1. The significance of this deviation was around 3 sigma, a 99.7% chance it wasn't a fluke. In particle physics, you don't pop the champagne until 5 sigma, but in cosmology, 3 sigma is enough to induce insomnia. If April 2024 was the tremor, March 2025 was the earthquake. DESI released its Year 3 data, covering nearly 15 million galaxies and quasars. Many expected the anomaly to vanish, a common fate for 3 sigma signals as more data averages out statistical noise. It didn't vanish. It sharpened. The new analysis, combined with high-precision CMB data from the Planck satellite and supernova data from the Pantheon Plus sample, pushed the preference for evolving dark energy closer to 4 sigma. The narrative that emerged was consistent and startling. Dark energy is not a stiff, unyielding constant. It is dynamic. It is thawing. The implications are physical, not just mathematical. If W is currently rising above -1, With estimates sitting around -0.85 in the present epoch, the repulsive force is weakening relative to gravity. The accelerator pedal is being eased off. While DESI stared from Arizona, another eye opened in the darkness of space. The European Space Agency's Euclid telescope, launched in 2023, resides at Lagrange Point 2, a million miles from Earth. Euclid's mission is complementary to DESI. While DESI focuses on spectra and redshift, Euclid focuses on shapes. It measures weak gravitational lensing, the tiny distortions in the shapes of background galaxies caused by the mass of foreground dark matter. This tells us how clumpy the universe is. In a universe dominated by a rigid cosmological constant, structures grow at a predictable rate. If dark energy is weakening, gravity gets a slight upper hand in the recent epoch, allowing structures to clump faster than expected. In late 2025, the Euclid Consortium released its first quick-look cosmological constraints. While the full 6-year survey is years away, the initial sample of 26 million galaxies showed a growth rate of structure that aligns uncomfortably well with the DESI findings. The universe is slightly clumpier than a pure lambda CDM model predicts, consistent with a dark energy that is losing its grip. We now have two independent heavyweights, one on the ground measuring expansion history and one in space measuring structure growth, pointing toward the same conclusion. The vacuum is changing. If dark energy is not a constant, what is it? The leading candidate is a scalar field, often termed quintessence. Unlike the cosmological constant, which is a fixed number in Einstein's equations, a scalar field is dynamic. It can roll. Imagine a ball sitting at the top of a hill. This is potential energy. If the ball is stuck there, it acts like a cosmological constant. But if the ball starts to roll down the hill, its potential energy changes. This is thawing quintessence. The field was frozen by friction in the early universe due to the high expansion rate, but has recently come unfrozen and started to roll down its potential curve, losing energy density as it goes. Theoretical physicists, particularly those in string theory, are secretly delighted by these results. For years, string theory has struggled to accommodate a positive, constant, cosmological constant. The swampland conjectures, a set of criteria proposed by Kamran Vafa and others, suggest that a true, stable de Sitter vacuum, a universe with constant positive lambda, is impossible in a consistent theory of quantum gravity. According to the swampland program, scalar fields must roll. A constant lambda is an unnatural anomaly. The DESI and Euclid results are the first observational evidence that the swampland might be real. The universe is rejecting the unnatural state of constancy. However, the data contains a puzzle that keeps theorists awake. To fit the observational history, the equation of state seems to have crossed the phantom divide. It went from W less than -1, or phantom, to W greater than -1, or quintessence. Standard scalar fields cannot easily do this. Crossing -1 usually requires exotic physics, such as quantum models, which combine quintessence and phantom fields, or modifications to general relativity itself, like Horndeski gravity. The universe isn't just rolling. It might be doing a loop-de-loop. The most existential question arising from the waning vacuum is, what happens next? Under the old lambda CDM model, the future was boringly infinite. Expansion would accelerate forever. But if dark energy is a rolling field, we must ask where it is rolling to. There are two main scenarios currently being debated in light of the 2025 data. The first is the 0-point settle. The field rolls down to zero potential energy. The acceleration stops. The universe continues to expand due to inertia, but gravity slowly breaks it. We end up in a cold, coasting universe, but not a ripped-apart one. The second scenario is the negative dive, also known as the Big Crunch. This is the scenario that has captured the public imagination. If the scalar field rolls far enough, it could pass zero and become negative. Negative dark energy is attractive, not repulsive. It acts like supergravity. If the current trend of weakening continues linearly, we could see the acceleration stop within a cosmic blink of an eye, perhaps 10 to 20 billion years. Once acceleration stops, if the energy density flips negative, the expansion reverses. Distant galaxies would turn around and rush toward us. The redshift would become a blue shift. The cosmic background radiation, currently a cold microwave bath, would begin to heat up. The universe would contract faster and faster until all matter, energy, and spacetime collapse into a singularity. Professor Young-Wook Lee of Yonsei University, a vocal critic of the Standard Model, has pointed out that this cyclic possibility restores a certain philosophical elegance to the cosmos. No longer a one-and-done explosion into nothingness, the universe may be a heartbeat, expanding and contracting in an eternal rhythm. There is a silver lining to this upheaval. It might solve the biggest headache in cosmology, the Hubble tension. For a decade, we have had a discrepancy in measurements of the Hubble constant, the current rate of expansion. Measurements from the early universe via Planck predict about 67 kilometers per second per megaparsec. Measurements from the local universe via supernovae and Cepheids measure about 73. The gap is statistically unbridgeable. However, these measurements assume the standard lambda CDM model to connect the early universe to today. If you introduce evolving dark energy, specifically a version that was stronger in the past, the phantom phase hinted at by DESI, you change the expansion history. This early dark energy or dynamical behavior can bridge the gap, effectively raising the CMB prediction to meet the local measurements. The waning vacuum might not just be a new discovery, it might be the missing piece that makes the rest of the puzzle fit. It is important to ground this excitement in scientific caution. Extraordinary claims require extraordinary evidence. While 4 sigma is compelling, it is not proof. Skeptics argue that the signal could be a systematic error. Perhaps we don't understand the dust in our own galaxy as well as we think, affecting the brightness of supernovae. Perhaps the evolution of dark energy is actually an evolution in the properties of the galaxies we are using as standard rulers. Furthermore, the phantom crossing, where W dips below -1, is physically problematic. It implies a violation of the null energy condition, suggesting vacuum states that are unstable. Many theorists prefer to think the data is slightly off, rather than accept that the universe is unstable at a quantum level. The look elsewhere effect is also a factor. When you look for deviations in many different parameters, you are bound to find one by chance. Is the weakening signal just a statistical fluctuation that will wash away with DESI Year 5 data? It is possible, but the corroboration from Euclid makes this fluke hypothesis harder to sustain. As we look toward the remainder of 2026, the scientific schedule is packed. Euclid Data Release 2 in late 2026 will be the big one. It will contain deep cosmological parameters derived from weak lensing over a much larger sky area. If Euclid confirms the weakening of W to high precision, the Lambda CDM model is dead. Meanwhile, the Vera C. Rubin Observatory, a ground-based giant in Chile, is coming online. It will find more supernovae in a few years than humanity has found in all of history. It will provide the standard candles to cross-check DESI's standard rulers. We are living through a paradigm shift. For a generation, we taught students that the universe was dominated by a cosmological constant, a simple, boring number. We were wrong. The universe is far more interesting than we gave it credit for. It is dynamic, evolving, and perhaps finite. The vacuum is waning, the accelerator is easing up, and for the first time in human history, we can credibly ask, will the universe end in fire, rather than ice? The data says, don't buy your winter coats just yet.